Friends, we're back again. We're working with very slightly soluble compounds and solubility product equilibria. This time we have a little bit tougher of a problem than we saw before, even though it's asking for the same things. It says find the solubility of silver sulfate and the concentration of each individual ion. The tough part for this is the fact that we won't have all one-to-one ratios like we did before. So if I look at silver, silver is Ag plus, sulfate is SO4 2 minus, and I need two Ag pluses to balance off the charge of sulfate. And so if I am asked to write the balanced chemical equation for this, it's going to look as follows. Ag2SO4, a solid, is in equilibrium with its ions, which are Ag plus, aqueous, and SO4 2 minus. But to keep this balanced, I need to have a coefficient of 2 in front of Ag plus. So when I write the equilibrium expression for this reaction, I get Ksp is equal to the concentration of Ag plus, but it's also squared because of that coefficient, multiplied by the concentration of SO4 2 minus. Ratios are so important in these problems. And so when I go to solve this and I say, if I'm asking about solubility, we call the whole compound X, and it has a coefficient of 1. That means that SO4 2 minus would also be X in solution. But Ag plus is actually going to be 2X. There are going to be twice as many Ag plus ions as there are SO4 2 minus ions in solution. This usually brings up a very important question for students. Am I using this coefficient right here? Am I using it twice? And the answer is absolutely you are, but for very different reasons. Here we're using the 2 as what we would call kind of a stoichiometric ratio between the two ions in solution. Here, as part of our equilibrium expression, all concentrations are raised to the power of their coefficient. So you do use it twice. That leads to some interesting math, as we'll see here in a minute. But before we do, we need to know what is the value of silver sulfate's equilibrium constant. So if I look over here, here is silver sulfate, Ag2SO4, 1.5 times 10 to the minus 5. That is its value. So let's plug that in. We have 1.5 times 10 to the minus 5 is equal to, this is where I've got to be very careful, 2x squared times x. If I've seen it once, I've seen it 1,000 times. Someone gets into kind of a hurry, their math gets a little bit sloppy. So be very close, or be very careful here. 2x all squared is actually 4x squared, right? You don't just square the x, you square the 2 as well. So I have 4x squared here times x. Long story short, 1.5 times 10 to the minus 5 is equal to 4x cubed. Now, if I want to solve that, the very first thing I've got to do is take both sides and divide them by 4. So if I say 1.5 e to the negative 5 divided by 4, I get a very small number, 3.75 times 10 to the negative 6. That's equal to x cubed. So I've got to take the cube root of both sides of this equation, and I'm going to put it over here. X is equal to, again, the cube root of 3.75 e negative 6. I do that, I get x is equal to 0.016 molar. This x value is actually known as the solubility of the compound silver sulfate. X is also equal to the individual concentration of sulfate, SO42 minus. And so it is 0.016 molar. Here's another place where we have to be careful, though. A lot of times I'll see students that will, to get Ag's concentration, they'll multiply the solubility by 2 and then square it. That's not what we're about in this case. The solubility, or I should say the concentration of Ag plus is just 2x. It's not 2x squared. We had to square Ag plus in the equilibrium expression, but it's just Ag plus is 2x for its solubility. So we get 0.032 molar. Now, I'm not confident that my calculator is all that great, or at least I'm not great with it. So if I wanted to check my work, here's what I would do. I would just plug those numbers back into the equation. So I would say KSP is equal to 0.032, it's Ag plus concentration, squared times 0.016. And if we're lucky, that means our KSP value, or we should get our KSP value or close to it. So I'm going to say 0.032 squared times 0.016. And I got KSP is equal to 1.6 times 10 to the minus 5. You may say, well, Mr. Lau, that's not the same as 1.5 times 10 to the minus 5. It's pretty darn close. It's just a rounding error that gives us that result. So close enough for us. Okay, let's come back together and let's practice one that's kind of like this. And then afterwards, I'll have you do one that is completely unfamiliar. See you soon.